You are listening to Climate Now. I'm Katherine Gorman.
And I'm James Lawler.
And today we are investigating the world of biofuels.
Where they come from, what percentage of our energy supply they represent today, and how that might change in the future.
And with us to walk us through all of those questions is Dr. Matthew Langholtz. He's a natural resource economist at the Bioenergy Group at Oak Ridge National Laboratory. So, Matt, thank you so much for taking the time to talk with us today.
Thanks for the opportunity.
So, Matt, we ask all of our guests the same question first. How did you get where you are today?
So I got my undergrad degree in forestry, just kind of grew up interested in the environment, everything, holistically speaking. Peace Corps after college, Paraguay, agroforestry, sustainable development, soil conservation, forest conservation kind of stuff. Grad school, more forestry, sustainable forestry, forest economics, agroforestry, short rotation woody crops, that kind of stuff. And just interested in the potential for sustainable natural resource use.
Very cool. So let's start with the basics. You've been the lead scientific author on several important studies on the economic availability of biofuels. And we're excited to explore with you what biofuels are and how effective and reliable they'll be in the future. But first, let's get to the very fundamentals. Can you walk us through what biofuels are, or rather biomass? Let's be even more basic. What is biomass?
So generally speaking, biomass is anything that is or was alive, any organic material. And that might have kind of slightly different connotations in different contexts or different sciences. But in this context, it's pretty much plant material or even some wastes or some other kind of organic materials that could be used to make energy.
So, for example, to put all of this, the conversation of biofuels into perspective, give us a sense of, scale. How much energy do we get today from coal, oil, natural gas, nuclear energy, and renewables? And then, within that renewables bucket, biofuels.
Yep. So the US uses about 100 quadrillion BTUs per year, British thermal units per year. So conveniently, it's about 100 quads per year.
And that's our total energy supply?
Total energy consumed. On the supply side, interestingly, in 2019, we produced slightly more than we consumed for the first time in about 50 years. So in 2019, we produced 101 quads approximately and used about 100 quads. Last year, there was a little dip. Things went down to like 96 quads with the economic contraction, but we could call it over the past 2 decades or so, about 100 quads per year used and now approximately consumed and produced now.
Got it.
And I could go into the breakdown a little bit if you want.
Yeah.
So of that 100 quads produced and consumed in the US, about 80 are from fossil energy. So those 80 quads from fossil, about half of that is from natural gas, followed by oil and coal. And then a little more than 10 quads are from renewable energy, and a little less than 10 quads are from nuclear. So it's about 80% fossil, 10% renewable, 10% nuclear.
So I think that's interesting. We hear all this talk about renewables, but so far, they only represent about 10% of the energy supply that we're currently using. And of that 10%, then, what percentage is biofuel?
40%.
40%. Got it. And in addition to that, of course, you have all the others. So wind, hydro, solar. And so is it right then that biofuel constitutes the largest piece of the renewables pie of that 10%?
That's right. Yep. So of those 10 quads, about 4 or 5 from biomass, about 3 each from wind and hydroelectric, and about 1 quad from solar. And this is all from US Energy Information Agency's annual energy review.
And so when we talk about the economic availability of biomass, can you explain what that means?
Yeah. So that economic availability is a term that we picked up to help specify what we mean by potential supply. When we think about biomass supply in the U.S., there's some huge supply out there, but some subset of that is available within certain environmentally sustainable criteria, and some subset, maybe overlapping subset of that, is also technically available, like within our current logistical and operational potential. And some subset of that is what I call the economic availability. Basically, how much could a market afford? If you're trying to produce ethanol at say $2 or $3 or $4 a gallon, there's a limit to how much you can pay for your biomass feedstock. So there's a lot of biomass out there, but only some of it is sustainable, some of it's available, some of it is cheap enough, and only a subset of that would probably be commercialized, would be commercially successful.
And so, Matt, how do we then go from biomass, which is what we've been talking about so far, to biofuels? All of this biomass coming in from very different sources, as you've alluded to. How do we then get to something we can actually put into an engine?
The conversion side isn't my specialty, but generally, so that we have biofuels today. There's corn ethanol, and through fermentation, and just process of fermentation, kind of like making beer. It's used to make ethanol. On the cellulosic biomass sides, like we're talking about here, there's thermochemical conversion, so a combination of heat and chemistry to take biomass and convert it into liquid fuels and other products. There's biochemical conversion, again, kind of like the ethanol, a fermentation process.
And you mentioned earlier that 4 or 5 quads of our current renewable energy supply comes from biofuels. What type of biomass is used to produce those biofuels?
Pretty sure it's about 50-50 between biopower, which is largely industrial wood waste from the forest industry to make electricity, that they use some of it. They use some of the electricity in their processes and put some back into the grid. And then another big part of that, I could verify it, and anyone check me, but I think it's about 2 quads that come from the corn to ethanol to be blended with gasoline at the pump. And there's some other little things in there, but that's the bulk of it.
In 2016, you led a study in partnership with the U.S. Department of Energy called the Billion-Ton Report. And in this report, you and the other authors went into great depth on the sources of biomass and their economic availability across forests, wastes, agricultural resources, and surprisingly, algae. So do you think you could discuss what that economic availability looks like using current technology and infrastructure, and any other non-economic cost considerations to keep in mind as well when we think about these feedstocks?
So about a third of the US is in forest land, and about half of that forest land is considered by the US Forest Service to be productive enough to be considered timberland. So potentially productive enough to produce forest products. Forestry is a big topic. There's a continuum of forest land goals, management goals and priorities, ranging from forest plantations, where we try to kind of optimize for wood production, for pulp and paper, dimension lumber, houses, decks, etc., all the way to preservation on the other side, where we don't harvest anything to maintain ecosystem services. And there's everything in between, multiple use.
Now, you also worked with the University of Tennessee and the U.S. Forest Service to evaluate the potential availability of biomass resources in the U.S. Can you tell us what you found?
So after we exclude protected lands, protected forests, or sensitive forests and inaccessible forests, and using a model that accounts for the, different forests have different ages, and some potentially could be harvested, some potentially could be partially harvested or thinned, some are too young. So depending on your timber stand age class distribution, this kind of influences how much could be available, how much wood could be available, and how much biomass could be available at any year. But basically, accounting for the land base, accounting for sustainability constraints, accounting for conventional demands for your conventional forest products, we find that at $60 a ton roadside, there's about 100 million tons per year of wood that could be derived from forest thinnings and logging residues. So those are forest thinnings, trees that are less than 5 or 6 inches diameter, and logging residues, tops and limbs that are left in the forest after trees are cut down. By the way, that's less than 1% of the 15 to 20 billion tons of wood that's standing on timberland. So it's a tiny fraction of the total. It's a significant potential cumulatively.
And when we talk about roadside availability, what does that mean exactly? Where's this 1% coming from?
We're pretty much talking about like existing managed forests that can also produce biomass, that do produce biomass now, that largely goes unused. And, real fast, from a forest management perspective, we're talking about if there's a market support to remove biomass, then forest managers can remove small trees to let other trees grow bigger, avoid forest fires, which, as we've seen, have major costs in terms of homes and lives lost, improve forest health, active forest management includes harvesting and removals, and fuel load, forest fire, fuel load reduction, and things like this to improve forest health.
Got it. And so basically we're talking about forests that already have a timberland designation by the U.S. Forest Service. Is that right?
So there's, there are a lot of forest lands, basically in drier areas, that don't grow fast enough, where you wouldn't want to cut them down because they wouldn't grow back fast enough. I think it's 20 cubic feet per acre per year or something, some minimum production. Yeah.
And so what's required to extract that value that you and your colleagues identified? Is this an opportunity for private companies to set up shop, collect this unused wood, and cart it over to a processing facility, or is more required to actually see the benefit or actually realize this value?
So I guess first and foremost, you need the market to support it. Then you need the infrastructure built to use it, just like anything else. Just like any other current forest industry, where we have pulp and paper, chip and saw timber, a market for these products, and an industry that responds to it. If you have more price signals to use more of it, then you could. I guess one extreme example maybe is maybe not. I don't mean to say extreme, but an example of market demand in the UK, they have demand for CO2 reduction. They offer a price premium for wood pellets over coal. They have the Drax power facility in the UK, where we export about 5 million tons per year of forest thinnings and wood waste pelletized on barges that go to the UK, and they produce power in the UK with wood from here.
So you're saying it's worth it for a power producer in the UK to ship wood pellets on a barge across the Atlantic and burn them in a plant, as opposed to just using oil or some other local resource because of the price on carbon that they have there.
Exactly.
So that's interesting, because those boats that are taking those wood pellets across the ocean are not powered by clean energy, are they?
No, and I'll give you a study where they do the life cycle assessment, and because barge shipment is so energy efficient, it comes out ahead.
So you can ship a bunch of wood across the Atlantic and burn it for fuel, and it's still more carbon efficient than coal?
It's hotly debated, right? and we could get there. We could go there.
We don't have to go down that road, but it's sort of an interesting comparison, I think.
There's research that indicates that it's net carbon beneficial when compared with coal, and at the right carbon price signal, it's economically viable too.
Okay, so to summarize, I suppose there's this huge potential in the US to derive substantial amounts of energy from forest byproducts. Your team has identified how much that would be and what the price point could be as long as there's a market for it, say if we had some kind of carbon pricing scenario. But currently, there is no market for it. Is that right?
That's right. So biopower, so about half of that 4 or 5 quads is the biopower. That's mostly wood. So that super low hanging portion, that super low hanging fruit, the cheapest stuff is economically viable in the current market. And if you have more market signal, you could bring on basically more material.
Interesting. So in the billion ton report, you also name waste as another category of biomass. What is defined as waste here, and how available is it to use as a feedstock?
Yep. So waste is, in the billion ton report, waste is the most diverse category. There's a lot of different stuff in there. There's urban wood waste. So that's like power line trimmings and storm debris from urban areas. Municipal solid waste, which is basically your garbage, or the organic fraction of your garbage. There's secondary wastes, which is mill processing residues. So like nut processing, fruit processing, scraps from any kind of agricultural process, manures from confined animal feeding operations, fats, oils, and greases. So like industrial fat byproducts or grease byproducts or restaurant grease traps and things like this. So a lot of different types of wastes. I think it's viewed favorably because it's people like the idea of using something that doesn't have another use. So it has, I think, good public perception. It can have a negative cost, like potentially people are paying to get rid of it. Maybe you have to add cost to sort it. It might not be as simple to convert to a biofuel, depending on what it is. So a lot of potential in there. Probably some economic low-hanging fruit in there. A lot of it already used. On the fats, oils, and greases already goes a lot to biodiesel production. So the market works already where it can. I guess, again, if you added a price for a carbon neutral fuel from waste, then maybe some more of this could also be economically available. So in our billion ton report, we had about 100 million tons of forest land resources. That's at $60 a ton roadside. On the wastes, if we also could afford about $60 a ton, we'd get another 100 million tons from this big mix of waste resources.
Great. And the next category we have is agricultural waste. So agricultural resources and materials. This is different from the waste you were just describing, right?
Yep, different. So we've looked at the forest land base, we've looked at wastes. Now there's the agricultural base, so all of our ag land, which we look at separately. So resources from agricultural land, 2 big categories. One is agricultural residues. This is mostly corn stover. We also have wheat straw, forget what else, something else in there, but these agricultural residues that are left on the field. And the other is biomass energy crops. So looking at those residues first. So, there's some places where you have to leave the residues for soil conservation to avoid water erosion. There are other areas where there's not enough that it's economically viable to pick up. So about half of the supply maybe could be environmentally and operationally available. Maybe about 100 million tons of agricultural residues, most of that corn stover available at $60 a ton roadside.
So that's yet another 100 million tons from another source of biomass that's available. It's fascinating because the picture that you're painting, and correct me if this is wrong, but it sounds like with some adjustments on the policy side in terms of pricing on carbon, it could very well transform what we do with all kinds of already occurring materials and resources in our economy that right now they're just sitting there and we don't currently recognize.
Right, but if we did recognize it, I imagine this could create a sort of explosion of new businesses and jobs because we're going to need people to go out and collect all this stuff, to process it, etc.
It's really truly incredible that if we just tweak the price of carbon, biomass can become a considerably large source of sustainable and renewable energy.
You got it. Yeah. So the current bioeconomy, or at least when we looked in 2016, used right around 365 million tons a year. If you added 100 from forest, 100 million from forest, 100 million from waste, 100 million from ag, then you would almost double the current bioenergy sector already, just with those things that exist today. Those forest land resources that are, I would argue, underutilized today, waste resources that could be used today, agricultural resources, agricultural residues that could be used today. And I haven't gone into the biomass energy crops yet. So if you, so the biomass energy crops, so purpose grown biomass resources, that's kind of like this last terrestrial category. So again, we worked with University of Tennessee to model this potential supply. And this is another economic model that accounts for the land base, accounts for the current allocation to different crops.
So, when you say it counts for the land base, what does that mean?
USDA reports crop land and pasture land by county and the allocation of, say, corn, soy, cotton, wheat, etc., to each of those already. So there's already an agricultural land base of uses.
Okay, so it accounts for the reality of where these crops are already being produced. It's not hypothetical.
Yep, and it accounts for and the USDA projects demand for food, feed, fiber, corn ethanol, export. So accounting for the land base, accounting for projected demands, which kind of vary, the outlook varies year to year based on incomes in other countries that can affect diets in other countries, that can affect exports for animal feed in other countries. That affects our demand on our agriculture, and then you get a tariff in there that will throw things off, this sort of thing. But overall, doing our best to account for the current land base, the current resource base, projected demand, and in addition to that, the demand for the conventional food, feed, fiber, fuel, and exports, can you produce a little bit more biomass? We would target those biomass energy crops in ways that complement the agricultural landscape already. So some lands are better suited, say, for biomass energy crops. Some corn acres that might be a little bit more prone to erosion, or maybe higher slope, or maybe biomass energy crops could have some competitive economic and competitive environmental advantages because you don't have to plant them every year. You plant them once and harvest them every year for 10 years or something like this. So they do a good job at protecting the soil and maintaining vegetative cover. Anyways, you could produce another 400 to 700 million tons per year of energy crops. So basically, you could double our bioeconomy with the forest, waste, and ag. You could double it, you could more than double it again if you wanted to include biomass energy crops.
Wow. So now moving to the last category, which is algae. I'm kind of fascinated by algae for some reason. It seems like this infinite resource, but how does algae fit in as part of the current set of biomass feedstocks?
So there, you could produce microalgae, which is kind of a little freshwater algae that you could grow in ponds. That's what we looked at in the billion ton report. There's also macroalgae, basically seaweed, which also has a really interesting, I think, potential upscalability on the coasts. Both of these potentially can, their removal can potentially benefit the ecosystems by removing nutrient wastes. With the microalgae, we looked at production scenarios where we co-locate with CO2 sources, because if you add CO2 to the water, then the algae gets a yield bump. So we looked at scenarios where we locate the algae production with corn ethanol plants or coal or natural gas generation, electricity generation plants, where we capture the CO2 from those plants, use it to fertilize the algae ponds, increase the algae yields. So that's good. It's a way of recycling CO2 that comes out of an industrial process. A benefit of algae in these ponds is that you don't need agricultural land to do it. So there's no food versus fuel issue. A downside is that you have to construct this infrastructure to produce the algae, which can be really expensive. So for example, on the terrestrial side, all those resources were what might be available at $60 a ton. On the algae side, the lowest price we get is around $500 a ton. So an order of magnitude more expensive. Now, it's potentially algae has other benefits. It might be more easily convertible. It's just kind of, I think, a simpler biomass product that's more readily convertible to, say, a biodiesel. So it might be a higher value product, but it's a lot more expensive. You know, if we're looking at all of the above options, you know, and all of the above solution to our energy and CO2 problems, then everything needs to be considered, and probably everything has a place where it could be the best choice.
Yeah, and I'd love to touch briefly on the more widespread context of these things. What are the economic, infrastructural, technological barriers to the widespread adoption of biofuels in the US, and really globally in general?
So, you know, the first generation biofuels, of course, are here now. We have the starch-based ethanol that's at the pump. It's about 10% corn ethanol blended. Biodiesel has made significant gains in recent years. Brazil powers a lot of their transportation with ethanol from sugarcane. Germany and other countries power a lot of their vehicle fleet with biodiesel. In terms of what we're talking about in this conversation, the second generation biofuels from cellulosic resources, the wood, the wastes, everything you can't eat, agricultural residues and things like this. So we've been hitting on, I think, some of these constraints. A main constraint being it's hard to compete with $2 or $3 gasoline at the pump. But basically, cellulosic ethanol is modeled to be, it's probably looking at about $4 per gallon of gasoline equivalent. So if gasoline went to $4 or $5 a gallon, then second generation ethanol would probably be in the running. If you accounted for the CO2 benefit of a renewable fuel, then you could have a price premium on top of that price per biofuel, so you could afford to buy more biomass and afford to mobilize more biomass. I think of infrastructure barriers as economic barriers. So biomass is hard to handle. It's heterogeneous, it's fibrous, it's stringy. We're talking about bales of stuff rather than train cars of coal that's more energy dense and flowable and things like this. So it's just challenging. Compared to fossil, it's economically challenging to mobilize. But if we accounted for costs of greenhouse gas emissions, soil erosion, water quality, things like this, and find logistical ways to shave off the price, then biofuels, second generation biofuels, could start to compete more.
So, to what degree are biofuels net negative in terms of their overall CO2 emissions?
So the upshot is biofuels are not CO2 net negative. So biofuels don't remove CO2 from the air, but they do avoid adding new CO2 emissions from the air. So they're not net negative unless you add carbon capture and storage, or CCS, to the system. then it's net negative. So there's a really great hub out from John Fields and others at Colorado State. So this study looked at cellulosic biofuels and the net greenhouse gas benefit under a few different scenarios. Let's say we're growing switchgrass as a cellulosic biomass feedstock for biofuels. Your carbon benefit kind of depends what the prior use of that land was. So it's different if you grow switchgrass on ag land versus pasture land versus forest land. It wouldn't be viable from a CO2 perspective to cut down forest land and start growing switchgrass. But under some scenarios, if you take land, put it into switchgrass, every year that switchgrass absorbs about 50 or 60 tons of CO2 per hectare in the biomass. And if we use that biomass to produce ethanol, all of that CO2 is re-emitted to the atmosphere, so there's no net change, so it's not carbon negative. But in the process of growing that biomass, we produced about 900 gallons of ethanol, which is enough energy to displace about 500 gallons of gasoline, which would have emitted about 6 tons of CO2. So in that system, we didn't remove CO2 from the atmosphere, but we avoided putting about 6 or 10 tons of CO2 into the atmosphere. So that's the avoided fossil fuel emissions.
Now, you're also part of a group that did a large study on bioenergy paired with carbon capture and sequestration, also known as BECCS, BECCS. Could you summarize for us the key findings there in terms of the extent to which we can use these biofuels to create bioenergy and then use CCS technology to store even more carbon than what is emitted? How much would that cost, and how well does that concept scale?
So bioenergy can be biofuels or it can be biopower, like we were talking about. And you can take biomass, produce biopower, and use this CCS to capture CO2 out of the air and stick it back in the ground. The Intergovernmental Panel on Climate Change has a few different pathways to net zero CO2 by 2050. We were talking about our resource potential. 300 million tons exists today. You can add 400 million tons of energy crops, that sort of thing. If we use that resource base, use it to produce bioenergy with carbon capture and storage, what would the cost of that be? So there's been previous work on just that, estimating about up to about 700 million tons potentially of CO2 sequestered annually. And we took that spatial distribution, looked at the geological sequestration basins. It's kind of regionally across the country, and then accounting for distance and site suitability for doing this. And basically in the near term, using the near term resources, you could sequester about 200 million tons per year. If you had energy crops, you could sequester up to 700 million tons per year. We probably won't get to all that because there are other uses for this. Another way to put it in context is the IPCC pathway 2 says the world might need 1 billion tons of CO2 sequestered per year to achieve carbon neutral in one of their scenarios. Here you could do most of that from the US alone. So it's not everything. It's not enough for the solution, but it could be a key part of the overall decarbonization solution.
Dr. Matt Langholtz of Oak Ridge National Laboratory. A fascinating conversation, James. I just love thinking about this stuff on being able to dig into these topics.
Yeah, it's really, really quite eye-opening to consider how far just, a little innovation can go, pairing what we already know how to do with biofuels and carbon capture, and that pairing with BECCS could get us to 700 million tons of sequestered carbon per year in the U.S. Alone, if we had sufficient carbon pricing. So perhaps, a brighter future is not as far off as we sometimes think.
Well, that is it for this episode of our Climate Now podcast. You can check out our other interviews, watch our videos, and sign up for our newsletter at climatenow.com. And if you want to get in touch with us, email us at contact@climatenow.com or tweet us at WeAreClimateNow. Hope you'll join us for our next conversation.